Hello everyone and welcome to the Science Scoop. Today, we're diving into one of the most profound mysteries of the universe, dark matter and dark energy. Together, these two enigmatic forces make up 95% of the universe, yet we barely understand them. How do they shape the cosmos? Why are they so important? And could they hold the key to the universe's ultimate fate? Stick around as we unravel these cosmic enigmas. To start, let's take a quick look at what we know. Everything we can see, planets, stars, galaxies, you, me, makes up just 5% of the universe. This visible matter or baryonic matter is the stuff we're familiar with. But what about the other 95%? Scientists have discovered that this mysterious portion consists of two components: dark matter, which accounts for 27% of the universe, and dark energy, which makes up a staggering 68%. Now here's the mind-blowing part. Dark matter and dark energy are invisible. They don't emit or interact with light in any way, which is why we call them dark. How did scientists even figure out these components exist? That's where the story gets fascinating. Let's start with dark matter. Dark matter was first theorized in the early 20th century. Astronomers noticed something strange. Galaxies were spinning much faster than they should. According to the laws of physics, the visible matter in these galaxies didn't provide enough gravitational pull to hold them together. By all accounts, they should have flown apart. This mystery became more evident in the 1970s when Vera Rubin, a pioneering astronomer, measured the rotation of galaxies. She found that stars at the outer edges of galaxies moved just as fast as those near the center, something that defied all expectations based on visible mass. The only explanation? There must be some invisible massive substance exerting a gravitational force. And this is what we call dark matter. So what exactly is dark matter made of? Well, we don't know yet, but scientists have some theories. It could be made of exotic particles like WIMPs, weakly interacting massive particles, or axions, which interact with normal matter only through gravity. Detecting dark matter directly has proven incredibly difficult, and scientists have built massive underground detectors in hopes of catching even the faintest signals. For now, we can only observe dark matter indirectly through its gravitational effects. Without dark matter, galaxies wouldn't form, and the universe as we know it wouldn't exist. It's like the hidden scaffolding that holds the cosmos together. Now let's shift gears and talk about dark energy, which is even stranger. In the late 1990s, astronomers studying distant supernovae made a shocking discovery. The universe isn't just expanding, it's expanding faster and faster. This was completely unexpected because gravity was supposed to slow the expansion over time. Something was driving this accelerated expansion, and that mysterious force was named dark energy. What could dark energy be? One possibility is that dark energy is tied to a concept introduced by Einstein called the cosmological constant. He originally included it in his equations to balance the force of gravity, creating a static universe. But when the universe was discovered to be expanding, Einstein discarded the idea, calling it his biggest blunder. Now it's back in the spotlight. The cosmological constant suggests that dark energy is a property of space itself. As the universe expands, space creates more dark energy, driving further acceleration. Another idea is the quintessence model, which proposes that dark energy is a dynamic, evolving force rather than a fixed property of space. But here's the twist. Not everyone agrees that dark energy exists. Some scientists propose alternative models to explain the universe's behavior. For example, the timescape model suggests that the observed accelerated expansion might be an illusion caused by differences in how time and space behave in various cosmic regions due to time dilation. If this model is correct, it could mean that dark energy isn't required at all, it's simply a misunderstanding of cosmic measurements. These debates highlight how much we still have to learn about the universe. You might be wondering, why should we care about dark matter and dark energy? Well, these mysterious forces shape the very fabric of the universe. Dark matter acts as the cosmic glue that holds galaxies and galaxy clusters together. Without it, our universe would look completely different. Meanwhile, dark energy determines the fate of the universe itself. If the expansion continues to accelerate, it could lead to a scenario known as the Big Freeze or Big Rip, where galaxies drift so far apart that the universe becomes cold and dark. On the other hand, if dark energy turns out to behave differently than we think, it might slow down or even reverse the expansion, leading to a big crunch, where everything collapses back in on itself. Understanding these forces is crucial for answering some of the biggest questions about where we come from and where we're headed. So what's next? Scientists around the world are working tirelessly to unravel the mysteries of dark matter and dark energy. Advanced telescopes, particle detectors, and supercomputers are all part of this quest. Every experiment brings us closer to answers or raises new questions that push the boundaries of our understanding. And that's a wrap on today's deep dive into dark matter and dark energy. These cosmic mysteries remind us how much there is left to discover about the universe. If you enjoyed this video, don't forget to like, share, and subscribe. Drop a comment below with your thoughts or questions. What do you think about the timescape model or the idea of a universe without dark energy? Thanks for watching, and as always, keep exploring the cosmos.